Hey, how are you doing? Welcome to Classical Mechanics. As we said in the previous lesson, now it's time to study the case of the harmonic oscillator with friction and with periodic external forcing. Consider a spring of constant K in a medium that produces a damping of the form minus Bx dot and attached to a motor that applies a periodic force on the spring as F naught times the cosine of omega t. Omega is the frequency of the external forcing and F naught is the maximum intensity of this force. The differential equation for the motion of this system is x2 dots plus 2 beta x dot plus omega naught square x, where omega naught is the natural frequency of the oscillator, square root of k over m, and equal to F naught times the cosine of omega t. With the usual definition of constant, of course. Here omega naught and omega have nothing to do with each other. The former depends on the characteristics of the system, the spring constant and the mass, and the latter is an arbitrary frequency imposed on the forcing. We need to find a particular solution for this differential equation.
Make an educated guess.
Well, my educated guess is A times the cosine of omega t minus phi. I'm going to substitute my guess solution into the differential equation. First, I'll derive it once, minus A omega sine of omega t plus phi, and I derive it a second time, minus omega square A cosine of omega t plus phi. Then I substitute it into the differential equation. I will also use the trigonometric identities for the sine of alpha minus beta and the cosine of alpha minus beta. X2 dots. 2 beta x dot omega naught square x equal to F cosine of omega t. Here I apply the trigonometric identities. I'm gonna group terms in cosine of omega t first, and then those terms with sine of omega t. F naught minus A omega naught square minus omega squared times the cosine of phi plus 2 omega sine of phi times cosine of omega t minus A omega naught square minus omega square sine of phi minus 2 omega beta cosine of phi sine of omega t. Because sine of omega t and cosine of omega t are linearly independent functions, we can separate terms with sine of omega t and terms with cosine of omega t. From the sine term, we find that the tangent of phi is 2 omega beta over omega naught square minus omega square. So the sine of phi is, and the cosine of phi is. From the term with cosine of omega t, we obtain the expression for A. There's a little bit of wibbly-wobbly mathematical stuff here, so make sure to pause the video to make sure that you follow all the steps. So now we can write the particular solution as with phi equal to this particular solution is a periodic function. The amplitude of the position oscillates with the driving frequency, and the amplitude is given by this term, which also depends on the driving frequency. But as long as there is driving, there is oscillatory motion. The general solution is this particular one plus the homogeneous solution we found a while ago. Let's write again the homogeneous solution. E to the minus beta t times C1 e to the omega prime t plus c2 times e to the negative omega prime t. For times much greater than 1 over beta, the homogeneous solution is negligible. So only the particular solution survives. There is a transient behavior, and after that, a periodic motion. The amplitude of this periodic motion depends on the characteristics of the system. It depends on the damping, it depends on the natural frequency, and it depends on the driving frequency. But the frequency of the oscillations is just the driving frequency. The phase phi also depends on the driving frequency, on the damping parameter, on the natural frequency. But there's no dependence on the initial conditions here. That is washed out after the transient. The sinusoidal shape is distorted in the transient time. The constant function is modulated. But that disappears after the transient. Let's look for a moment at the amplitude of these oscillations. The amplitude is f naught divided by the square root of omega naught squared minus omega squared plus 4 times omega squared beta squared. We might want to find the frequency that maximizes this amplitude, and we do that by deriving the amplitude with respect to the frequency and making that equals to 0. That would be the frequency of resonance. So the derivative of the amplitude with respect to the frequency is this derivative and we make it equal to 0. Now we have the numerator equal to 0. I remove the negative sign from the beginning and then I divide everything by 4. Then I rearrange, I put the 2 beta squared to the right side and then I solve for minus omega squared, change the sign everywhere and then take the square root of that, and that is the frequency at resonance. That's the frequency that maximizes the amplitude of the oscillations. If there is little or no friction, then we have the amplitude explode. There is no dissipation of energy and the system absorbs it and the system can blow out. If we look at the phase phi, because omega is equal to omega naught, this implies that the phase shift is pi over 2, 90 degrees. The motion of the system lags the driving force by a quarter of a cycle at resonance. This means that when the particle is at its maximum position, the force being applied is 0. When the particle is at the origin, moving fast, then the force is maximum and in the direction of the motion. This optimizes the transfer of energy. The external force is applied when the particle moves faster, so it is being applied for a longer distance. This maximizes the work done on the system. No force is done when the particle moves really slowly, when the particle almost does not cover any distance. No force is wasted there. Here, at resonance, the force is in phase with velocity. Resonance has many interesting applications and many interesting dangers. We'll study some later in the course. As for now, may the science be with you.